All right, ladies and gentlemen, welcome to this third lecture on logic and set theory. I gave you a bit more time to recover from the weekly test of today. I hope you managed this time to upload your solutions properly. Actually, previous time we didn't see many problems there either. We know that it is stressful to write the test and also have to upload your solutions. We take into account that you need some time for that. In fact, we construct a test that we think should be doable in 35 minutes, so that it should leave you still 10 minutes to upload your solutions. Well, I hope that that actually works out like that. It is very unfortunate that we are in this situation that we have to do this online. So in previous years, actually, students were doing the test on campus, and then you don't have the extra complexity. You probably have seen my announcement of last Saturday, where I actually explained to you that, well, first of all, it's your responsibility to make sure that you have enough time to upload, and that you upload also your solutions in such a way that we can easily review them. But I also understand that you have to get used to the technicalities, and so what I also promised you is that we will only take into account your grade for the first weekly test, for the weekly test of last week, if you benefit from it, if your final grade benefits from it. All right, I would like to start this lecture today with a quiz question. And let me see whether my new system works here. I'm going to actually show you the quiz question like this. And it's a bit of a strange question, just to make you think about perspective. So you're cycling to the university and see a 1 euro cent coin lying on the ground. Question, do you stop to pick it up? And please go to menti.com, www.menti.com, and there you see the new code 4923908. Please let us know what you think. Will you pick up the coin if you're cycling and you see 1 euro cent coin lying on the street or not? All right, I see that 152, 154 students, we're going up still, have actually already answered the question. Let me wait 1 more minute. All right, let me show you the results so far. Of course, now you can still influence the results, but the vast majority of you say, no, I will not stop and pick up this 1 cent euro coin. It's not worth the trouble actually to stop the bike, get off my bike, pick up the 1 cent euro coin. Well, why am I showing you this? Because we had a couple of discussions with students about the last test, who were actually complaining about that they lost 1 point for a certain answer. Then we tried to and they were focused on how many points they got rather than on what they did wrong or and what they did right, and what they could learn actually from the test. What I'm trying to say is here, please be aware that one point on the weekly test has at most an influence of 0.06 points on your final grade. So it's really not worth spending your efforts on getting a higher grade. It's much more useful actually to use the weekly test to learn from your mistakes, to see what would have given you a perfect score, perhaps, by looking at the solution in the grading description, things like that. So, and by the way, this is also why we have the weekly tests. This is not for the purpose of assessment, really. It is really for actually letting you learn from your mistakes and giving feedback. So let me show my face again. I think you have seen the results of the poll. See things in perspective. Try to learn from the feedback, because that's the whole purpose of the weekly tests. They count for only very minor part of your final grade. So you really are not going to fail the course because of the weekly tests. I think you're going to pass, or many of you are going to pass the course because there are weekly tests. All right, how do you deal with this situation of the weekly tests? Please, well, when we have published the results, go to the weekly test, go through your own answers, try to compare them with the solution that we provide via the grading description, and carefully read the feedback of the student assistants and try to find out what you can improve next time. All right. After this, fatherly advice, let us move into the topic of today, and that is we are going back to derivations. Let me show you my slides again. We're going to continue our discussion of flag-style derivations, and in particular, we are going to discuss rules that allow you to deal with quantifiers. So universal quantifiers and existential quantifiers. That will be the first topic of today, and the second topic of today will be to discuss the application of derivations or of proofs and logic in the context of set theory. So we're going to make a start with the topic of set theory, discuss what is a set, and also how can you reason about statements pertaining to sets. All right, let me, I have a couple of videos for you today. I realize that seeing those videos, well, it's not easy to see them the first time. They go really fast. They're actually more designed to let you to allow you to pause the video so now and then, so that you can reflect on what is being said. So I'll limit the number of videos that I'll show today and selected a couple of which I think that you can get the most important points out of them without stopping the video. Don't worry if you don't get every detail in a video that I show. I'll return to the video and also show examples live on my here virtual Blackboard. For the first video, what you need to try to understand is what is the motivation behind the rules for universal quantification that we're going to have in a bit. The rules themselves I'll discuss in more detail live in the live lecture. There we go. In this lecture we will present introduction and elimination rules for universal quantification. Recall our intuitive explanation of universal quantification. We've explained universal quantification by saying that, well, universal quantification embeds the device computing truth values for the predicate Q into a larger device, connecting the input port of this smaller device to a so-called generator that generates values in the domain of the universal quantification, and connecting the output port of the device for Q to a so-called universal verifier that monitors whether it only sees ones appear on the output port of the device for Q. Clearly, this device would need to try every possible value in the domain of the universal quantification before it can produce an output. It does suggest immediately a strategy for proving universal quantification. To prove a universal quantification, the predicate in its body should be established for every element satisfying the domain predicate. But you may already realize that this is not a very feasible strategy if we would need to consider an infinity of cases. Let's illustrate this by means of an example. Suppose that we want to prove the statement x squared minus 1 is not equal to 0 for all integers x greater or equal to. Then we might start to consider all individual cases. So we might start with considering the case x is equal to 2, then indeed 2 squared minus 1 is equal to 3, which is not equal to 0. So in this case, the statement holds. Similarly, if x is equal to 3, then a computation will immediately reveal that x squared minus 1 is not equal to 0. Similarly, for x is equal to 4, and for x is equal to 5. So now we have considered 4 cases, but there are infinitely many cases. So this proof that this argument that you see here does not cover all possible cases. Now we should resist the temptation to say that, well, now you continue in this way and then you have a proof. Because actually we should not consider, or a proof should be a complete and convincing argument that the statement is true and not just consider a few cases. So this here is not a proof. Let's illustrate the difficulty or the problem with the situation of considering only a subset of cases by entering into a digression. And the digression will illustrate the importance of considering really every case. Let's consider a method for cutting a cake into pieces. The method works as follows. We put several marks at the edge of the cake and cut from every mark to every other mark, as you see here. Then you may ask, assuming an optimal placement of a certain number of marks, could we perhaps express the number of pieces one gets in terms of the number of marks one places on the edge of the cake? Let's consider this question for a number of cases. Using 2 marks yields 2 pieces. Using 3 marks yields 4 pieces. 4 marks yields 8 pieces. And you may now observe that at least so far the number of pieces is a power of 2. In fact, it is 2 to the power of the number of marks minus 1. So we can now formulate the conjecture that if we optimally place x marks on the edge of the cake and we cut, then we obtain 2 to the power x minus 1 pieces. Such a conjecture needs a proof, and suppose that we would proceed by considering individual cases. We have basically already considered the cases x is equal to 2, x is equal to 3, and x is equal to 4. And if we place 5 marks, then we get 16 pieces, and 16 is 2 to the power 5 minus 1. So also, if x is equal to 5, then our conjecture is correct. After having verified our conjecture in 4 cases, it is now perhaps tempting to conclude that the conjecture is true for all x. But we should resist the temptation. We have not yet considered all cases in detail, so we do not have a complete proof. And indeed, there is a surprise when we consider the next case. If we optimally place 6 marks, for instance as you see here, then we get only 31 pieces. 31 instead of the expected 32. So our conjecture fails when x is equal to 6. And therefore, the conjecture, which universally quantifies over all integers x greater or equal to, is false. This concludes our digression, which should have convinced you that trying to prove a universal quantification by considering just a few example cases individually is not a viable strategy. Let's return to our original example. We were trying to prove that x squared minus 1 is not equal to 0 for all integers x greater or equal to. And we have now clearly seen that considering a few cases does not constitute a decent proof here. A good proof for this statement proceeds as follows. To prove the statement for all integers x greater or equal to, instead of considering individual cases, we shall try to give a general argument that works for all cases. The argument starts by declaring an arbitrary integer x greater or equal to. Then we note that x squared minus 1 can be written as a product of x plus 1 and x minus 1. This property holds for all integers x. Now, since the product of 2 integers is 0 only if at least one of the factors is 0, it follows that x squared minus 1 is 0 only if x is equal to minus 1 or x is equal to 1. Recall now that we have assumed that x is greater or equal to. Therefore, we may conclude that x squared minus 1 is not equal to 0. Note that we deal with universal quantification in this proof by declaring an arbitrary integer x greater or equal to. We do not assume anything else about this x. So we don't assume that it is a particular value, it's just an arbitrary value greater or equal to. You can think of it as a variable. The rest of the argument explains why x squared minus 1 cannot be 0 under these conditions. Inspired by the example, we shall now formulate the preferred strategy for proving a universal quantification. To prove a universal quantification, it suffices to establish the predicate in its body, here q, for a variable, x, of which the only thing we assume is that it satisfies the predicate of the domain, p. Let's formulate this as a derivation rule. To prove the universal quantification, all x satisfying p also satisfy q, we declare a variable, assume that it satisfies p, and then try to establish that it also satisfies q. If that succeeds, then we may conclude the universal quantification with an application of the universal quantification introduction rule. Note that the derivation establishing that x satisfies q can be thought of as a general argument that would work for every particular element in the domain specified by p. The variable x satisfying p is temporarily added to the context, and it is important that it's new. It should, for instance, not already have been declared previously in the derivation and still be valid, and it should not clash with other objects relevant for the derivation. Note that the declaration of this variable is withdrawn from the context upon the application of the associated universal quantification introduction rule, as indicated by the ending flagpole. Let's now discuss how we can use a valid universal quantification in a proof. We also first illustrate this principle by means of an example. Consider the universal quantification for all real numbers x greater than 2. It holds that x plus 1 divided by x minus 1 is between 1 and 3. What can we do with such a universal quantification? Well, we can conclude for any particular real number a greater than 2 that a plus 1 divided by a minus 1 is between 1 and 3. So, for instance, we can conclude for the real number 5, which is greater than 2, that 5 plus 1 divided by 5 minus 1 is between 1 and 3. And we can conclude this directly from the universal quantification. Similarly, pi is a real number, pi is greater than 2, so pi plus 1 divided by pi minus 1 is between 1 and 3, and so on. Now we can formulate the general principle for using a universal quantification in a proof. From a universal quantification, we may conclude that any particular value satisfying its domain predicate also satisfies the predicate in its body. And let's formulate this as a derivation rule. If the universal quantification stating that all x satisfying p also satisfy q is valid, and in our proof there is a certain valid object a of which we can show that it satisfies p, then we may conclude that the object a must also satisfy q by an application of universal quantification elimination. An important condition for the applicability of this rule is that the object a somehow exists, either as a known value or in the form of a variable with the declaration still part of the context. The main message of this lecture is that to prove that some property holds for all objects of a certain kind, it's not enough to only consider a few example cases. It would of course be enough to consider all cases individually, but when there's an infinity of cases, this is of course impractical. A good alternative is given by the universal quantification introduction rule. It amounts to declaring an object or a variable satisfying the domain predicate and then establishing for this arbitrary object also the predicate q, the body predicate. You can think of this as a proof that can be instantiated to any value satisfying the domain predicate p. And therefore it is a general argument that works for all possible values in the domain of the universal quantification. The rule we have presented for using a universal quantification in a derivation may appear to be somewhat simpler. To use a universal quantification, we just have to have an object A satisfying the domain predicate,
And then if we find such an object, then we may conclude that this object will also satisfy the body predicate Q. But you should be careful when applying this rule. It is very important that this object A used in the application of the rule is a valid object. It should already exist. You should not invent it on the spot. We will come back to this issue in a later lecture. This concludes our discussion of the rules for universal quantification. In the next lecture, we will give an example of their application. And after that, we will discuss existential quantification.
Okay, ladies and gentlemen, that was the first video of today. I can tell you that I have one more video also about existential quantification and two about sets, so it will be very limited. The important message of the video that you should get is sort of repeated in the following quiz, in a following quiz question. So now to prove the statement, every even integer greater than 2 is the sum of 2 primes, would it be enough to prove that 4 is the sum of 2 primes, 6 is the sum of 2 primes, 8 is the sum of 2 primes, 10 is the sum of 2 primes, and 12 is the sum of 2 primes? Please enter your votes in Mentimeter at 4923908. Okay, your votes are still coming in. I'll give you 1 more minute to decide. All right, let's see the results. Let me show the results of the poll. And I'm pleased to see that the vast majority of you actually say, no, this is definitely not enough to prove actually this is a statement of Goldbach's conjecture. It's an open problem of mathematics. It's perhaps one of the most famous open problems actually. And giving a proof of Goldbach's conjecture has been a challenge for long. But for instance, to give you a couple of examples, so in 1938, this conjecture had been verified for all even numbers greater than 2 and less than 10 to the power 5. So that's and manually without computers. And so in 2013, as you can read on the Wikipedia page about Goldbach's conjecture, it has been verified for all numbers up to 4 times 10 to the power 18. But does that mean that we know that it is true? Definitely not, because even if you have proved the Goldbach's conjecture for the first 4 times 2 to the power 10 to the power 18 numbers, then still there are infinitely many numbers left for which you still need to prove it. So that's definitely not a way to prove this kind of conjecture. The video introduces a different kind of proof of this kind of a universally quantified statement. And I'll show you the rule again that you've also seen in the video. So the rule looks like this. So if you want to prove a universal quantification, if you want to prove for certain predicates P and Q that for all x that satisfy P, that all these acts also satisfy Q, then according to the rule, it is enough to declare, or then the strategy is to declare an arbitrary integer, or sorry, an arbitrary element, not integer, an arbitrary element satisfying the predicate P, and trying to prove for that arbitrary element satisfying P that it also satisfies Q. And note the 3 dots in the middle of the rule. That indeed indicates, okay, you get this flag, you get an extra assumption, you actually declare an element satisfying P, satisfying that is in the domain of the universal quantification. And now the goal is to actually prove that it also satisfies Q. And the 3 dots indicate that there should still be a proof, a derivation there's a derivation to complete at that place in what you see. All right. So I have another quiz question for you. Let me show that to you. Let me do that sort of smoothly. So now, and that's not this one, but I should make sure that you can vote. So now, suppose that we know that the following statement is true. So every even integer greater than 2 is the sum of 2 primes. Right? So basically what I'm saying is, suppose that we know that Goldbach's conjecture is true. Could we then conclude that 16 to the times 10 to the power 301 is the sum of 2 primes? Please enter your votes. And again, I should of course emphasize that we don't know whether it is the case that every even integer greater than 2 is the sum of 2 primes. But here you have to work under the assumption that somebody at some point in the future manages to prove Goldbach's conjecture. The question is then, could you draw the conclusion that is written on the slide? And I'll give you still half a minute to think about it. All right, let me show you the results. So the vast majority says yes. That means that you have understood how you could actually use a universally quantified statement if you know that it is true. And that is also sort of, this is also leading up, of course, to the rule for universal quantification elimination. So indeed, and this is also the correct answer, yes, you can actually conclude that this number is the sum of 2 primes if you know that the universal quantification is true. Let's consider yet another question. Suppose now that we know that the same statement is true, can we then also conclude that 16 times 10 to the power 301 plus 1 is the sum of 2 primes? I'll give you another half a minute to find the answer, to enter your answer on Mentimeter. Okay, so let me publish the results. And now indeed the answer is no, as most of you realize. The point is, if you want to use a universal quantification, then you can only use it for elements that are actually in the domain of the universal quantification. So in this case, the domain is even integers greater than 2. Now, 16 times 10 to the power 301 is an even integer, so 16 times 10 to the power 301 plus 1 will be an odd integer. It will not be in the domain of the universal quantification, and so the statement doesn't apply to this formula, to this number. You cannot use the statement to conclude anything about this number. All right, so this leads up to the rule for universal quantification elimination. Let me show you the rule. So if you want to, oops, that was the wrong, I should move my pointer there. Okay, so if you want to prove that, if you want to use that, or you know somewhere in your derivation, in the present context of your derivation, you know that the statement for all x satisfying p they also satisfy q holds. So this universal quantification somehow has been derived, or it has been assumed. That is also a possibility. Then by itself you cannot yet do anything with that. But if you also find somehow a declared object in your proof, say A, that satisfies the domain predicate, that satisfies P, then you can apply universal quantification elimination and conclude that that also Q holds for this A. Now there are a couple of, and this rule you would apply from top to bottom. There are a couple of things that we need to realize here, that this A that is mentioned in the universal quantification elimination rule should be an object that is already known, that has already been declared, that exists in the derivation. And so it could either be an object, this proof could be about numbers, and A happens to be a concrete number, or it can be a variable that was declared previously, and that is still, of which the declaration is still valid. We're going to see examples of this, but I already want to warn you that this is a very important and crucial element of this rule, that this A has to exist. And in particular, bound variables, and we'll get to that a bit later, bound variables, so as you can see them, for instance, in line K, so there you see an x, but this x is actually a bound variable. It's tied to this universal quantifier. That actually does not appear in the derivation as a declared object, so it has to be something else. We'll see an example in a bit later. Let me first move to the rule for existential quantification elimination and its reduction, and let us first see a video to introduce the ideas, and then we'll discuss in detail the rules.
The treatment of existential quantification is a bit special because the most commonly used technique for proving an existential quantification does not correspond to a sufficiently powerful derivation rule. In this lecture, we will discuss the derivation rules that correspond to the standard techniques for proving and using existential quantifications. These rules are based on the notion of witness. We will defer the discussion of the more powerful derivation rule for the introduction of existential quantification to a later lecture. We have explained the interpretation of existential quantification as follows. Starting from a device that evaluates the predicate Q, we have said that the existential quantification corresponds to encapsulating this device in a larger device, connecting the input port of the device for Q to a generator, which generates values satisfying the predicate P, the domain predicate, and connecting the output port of the device for Q to a so-called existential verifier. The generator starts producing values satisfying the predicate P, then these values are all input to the device for Q, and the existential verifier checks whether Q evaluates to true or false. If there's one value for which the device for Q evaluates to true, then the existential quantification should also result in true. We can call a value satisfying the domain predicate P for which the predicate Q evaluates to true a witness for the existential quantification. Let's illustrate the notion of witness with an example. Consider the existential quantification expressing that there exists an integer x such that x cubed minus 3x is equal to 2. A witness for this existential quantification is a value in the domain, here the set of integers, that also satisfies the predicate x cubed minus 3x is equal to 2. The number 2, for instance, is a witness, because indeed 2 is an integer, and 2 cubed minus 3 times 2 is 2. Note that the proof that 2 is a witness for the existential quantification that you see here is also a convincing argument that the existential quantification is true. Thinking of our device for evaluating existential quantifications, at some point the generator will generate the value 2, the predicate x cubed minus 3x is equal to 2 will evaluate to true, and the existential verifier will then output true. There is an alternative proof that the existential quantification shown here is true, because the number minus 1 is also a witness. Indeed, minus 1 is an integer, and minus 1 cubed minus 3 times minus 1 is 2. As an aside, you will probably have no trouble figuring out that minus 1 and 2 are the only two roots of the polynomial x cubed minus 3x is equal to 2, and hence 2 and minus 1 are the only two witnesses of this existential quantification. Based on the notion of a witness, we can now formulate a general strategy for proving existential quantifications. To prove an existential quantification, it suffices to prove that some value is a witness. We present the strategy in the form of a derivation rule. The rule is applied in the situation that we need to establish existential quantification. If we can prove for some object A that it satisfies both the domain predicate P and the body predicate Q, then we have actually established that this object A is a witness for the existential quantification. So then, we also have a proof for the existential quantification. The rule is referred to as existential quantification introduction. We put a star to distinguish it from the other existential quantification introduction rule that we will present in a later lecture. You may think of the star as referring to the notion of witness. It is important that this A, which is proved to be a witness as part of the proof of the existential quantification, is a valid object. It could be a value in the domain under consideration, but often it is a variable that has been declared previously. When the goal to prove the existential quantification is set, it is sometimes not yet clear what would be a suitable witness. In such cases, it is necessary to first do some forward reasoning and wait for a suitable candidate for a witness to present itself. As a consequence, the rule for existential quantification introduction is not merely a rule that is applied in backward reasoning mode. It usually requires both backward and forward reasoning, as indicated by the two-headed arrow. Let's now consider the situation that an existential quantification is valid in our proof. The mere fact that the existential quantification is valid implies that there has to exist a witness for it. The difficulty, however, is that we don't know which value is exactly that witness. This information is generally not revealed by the existential quantification. Nevertheless, we can make use of the existence of the witness, and we shall do so by simply declaring it as a variable. Suppose that we have a valid existential quantification in our derivation. Then by the starred version of existential quantification elimination presented here, we may declare a witness for it. We formulate the declaration with the sentence, pick an x with px and qx. You should understand this sentence as our way of declaring a variable x, of which we assume that it satisfies the predicates p and q. From now on, this new variable x may be used in the derivation, and moreover, we may use the facts that it satisfies p and q. As for any declaration, it is important that the declared thing is new to avoid confusion. So the x should not already refer to a previously declared object.
Right, I think I accidentally killed the video. I'm sorry for that. Let me not restart it. I was using a shortcut, and actually I was in the focus of my window was bad. Apologies for that. I think the motivation has been explained sufficiently in the video that you saw. You can also watch the rest of the video if you follow the link in the syllabus. I want to continue with a quiz question. Let's move to the following quiz question. Oh, there we go again, same problem. That is what I wanted to do. So here, so now what you have seen in the video is a motivation for what kind of strategy could you use when you want to prove an existential quantification. Now suppose that you want to prove the statement there exists integers x, y, and z such that x squared plus y squared is equal to z squared. Is it then enough to prove that 3 to the power 2 plus 4 to the power 2 is equal to 5 to the power 2? And I see you're already entering your answers on Mentimeter. That is very good. I'll give you, say, 15 seconds to complete your answers. Okay, let's show the results. Most of you actually say yes if you want to prove that there exist integers x, y, and z such that x squared plus y squared is equal to z squared, then indeed it is enough to prove that 3 squared plus 4 squared is equal to 5 squared. And why is that enough? Well, and actually that's also the correct answer. Why is it enough? Well, to prove an existential quantification, it suffices to find a witness. In this case, we need to have three witnesses because we need to find x. Then we have an existential quantification over x, y, and z. And these witnesses should be elements of the domain. In this case, the domain of integers, satisfying the equation. And indeed, 3 squared plus 4 squared is equal to 5 squared is a true equation, and therefore this proves the statement. Now let us move to back to the slides. Let me show you the rules, the rule that actually formalizes this proof idea. So to prove that there exists an x satisfying p and q, and this is how you would pronounce the existential quantification, it is enough to find a witness. And what is a witness? Well, it is an object A satisfying both p and q, satisfying both the domain predicate, so it needs to be in the domain, and it needs to also satisfy the predicate q. And this is a rule that you would apply, well, sort of as you have perhaps seen in the video also, that you apply from bottom, when you're reasoning from bottom to top. The idea is you apply this rule when the goal is to prove the existential quantification. But often you have to wait until you know what the A should be. It's a bit the same as with the false introduction rule. That's a bit inconvenient to apply because you typically don't know which predicate, which proposition P you want to use to establish the contradiction. In this case, the question is, what is the A that is going to be the witness satisfying both P and Q? Right? So in a way, the strategy that you should apply when you want to prove an existential quantification is wait until in your derivation you see what is a suitable object A. And it has to be said that sometimes some luck is needed. I mean, this rule does not always work in the sense that it's not always possible to identify a witness just like that. Well, that is a warning in general for this rule. I can tell you that in all examples that you will see in this course, the rule will work. So you don't have to worry too much about the fact that that you need some luck to be able to apply it. Okay, let me move to a next Mentimeter question. There it is. So what about, and let me also make sure that you can enter your answers. Now suppose that we know that there exist prime numbers p and q greater than 2, such that x is equal to p squared plus q squared. Can we then conclude that the number x is even? Please enter your answers. Well, think a bit about it. I'll give you 1 minute to enter your answers in Mentimeter. All right, a couple of more seconds. All right, let me show you the result of the poll. Well, you were divided about this one. And I have to say that perhaps this question was, the answer to this question is less clear-cut than to previous questions, because it also involves a bit of mathematics to actually draw the conclusion. It is a valid conclusion that x is even. And why is that? Well, if you take two prime numbers greater than 2, then those two prime numbers will be odd. Right? Number 2 is actually the only even prime number. So we have now, so if you take the square of an odd number, it's again odd. So now we add up two odd numbers, right? P squared is an odd number and q squared is an odd number. So, the result will be an even number. If you add up two odd numbers, you get an even number. Of course, there's more to it here than just applying existential quantification elimination. But what is the point of existential quantification elimination is that in a proof of this fact, you would first declare the witnesses two prime numbers p and q that actually satisfy the equation x is equal to p squared plus q squared, and then you start to reason mathematically about p and q. That's what happens, and for that you need the existential quantification elimination rule. Let me discuss the rule, and then we have a short break. Let me move back to the slides. So if you want to, so the question is, how do you use an existential quantification in a reasoning? If you know that, if you have proved, say, or you have derived that an existential quantification, there exists x, px colon qx is valid, then what you may do is say, okay, if this existential quantification is valid, I don't know at this moment perhaps what is the exact x that satisfies p and q, but what I do know is that there has to exist one. So what I can do now is to pick an x satisfying p and q. That's the idea of existential quantification elimination. And why is that useful? I mean, you may think that not much happens in this step. Well, this is useful because now you have declared an object x of which you know very little except that it satisfies p and q, and you can use that in the rest of your reasoning. And we'll see an example of that kind of reasoning later. What I have to add here is that the x that you declare by means of this pick an x with px and qx, this x has to be new. So it should not be an object that already occurs in your proof, because then there's confusion. I mean, it's not necessarily that object that occurs that also satisfies p and q. So you have to avoid that confusion and make sure that the x that you declare in line L is actually a new object. You can think of it as the witness for the existential quantification, and you can use it as such in the rest of your derivation. Okay, so for now, I would like to give you a 10-minute break. Let's reconvene at a quarter to, quarter to 4. So we reconvene at 15:45. All right, ladies and gentlemen, welcome back to the lecture on logic and set theory. This is the second part of today's lecture. We have already discussed rules for existential quantification and universal quantification. We are going to discuss in the second hour of the lecture. We are going to show an example applying each of these four rules that we have introduced. Before I get to that, let me tell you one more thing, and that is about that is about the bound variables. I was already alluding to that. There's a very special syntactic feature that we use to write existential universal quantifications. For instance, over here you see a universal quantification for all m a natural number, m plus n is greater than 6. This m, which is the blue purple square is trying to indicate that there is a sort of link between the m attached to the universal quantifier, the m in the domain predicates m and n, where it states that m is a natural number, and in the predicate after the colon, where it is stated that m plus n is greater than 6. Now, we say that this m is a bound variable in the universal quantification, and that means that, well, you should not think of this as, so the name of this bound variable in a way doesn't matter. Because if you look at this, this predicate, it's actually a unary predicate. There is no m intuitively in there. It's just a predicate on one thing, namely the n. So it expresses a property of the natural number n that you see over here. And so this this predicate will be true if this n is greater than 6, because then for every natural number n greater than 6, it holds that if you add another natural number to it, it still will be greater than 6. And it will be false if n is less or equal 6. Why? Well, because then you can always find a natural number, for instance 0, that refutes the statement. Okay? Now, changing the name of the bound variable, so changing an m consistently to a k in the universal quantification, does not really change its meaning, right? So also that predicate is true if n is greater than 6, and false if n is less or equal 6. So in a way, the name of the bound variable doesn't matter. And we shall use that property also in derivations. I'll get back to that in a bit. But what you should realize is that you have to be very careful how you do the renaming. Because look at this. So now suppose that we rename the k to an n, then something else happens. Then we turn a unary predicate, something that expresses a property of n, into a proposition. A proposition that states that basically is true if it holds that for all natural numbers, if you add this natural number to itself, you get something that is greater than 6. And of course, this is a false proposition, but it doesn't say anything about an arbitrary natural number anymore. It's a proposition, it's just false. It doesn't matter, I mean, you cannot fill in anything for the n because the n is now bound. So what this example is supposed to tell you is that you may rename bound variables, but you have to be very careful when doing so. In particular, you should not change the so-called linking structure. The variable that is bound by the universal quantifier, the k or the m or the n, I mean, there's a sort of relationship between the other occurrences of k, m, and n in the formulas that follow, and this binding structure should not change when you rename. All right, and now what does this have to do with derivations? Well, in derivations, we're going to assume that you always implicitly may rename bound variables. Only the bound variables, not the free variables, the variables that have been declared explicitly. I'll get back to that when we discuss an example. But it's actually the advice is actually to always do this, to make sure that to rename bound variables in such a way that you don't have 2 times the same bound variable. I mean that the same bound variable is not quantified twice, and we'll see an example in a bit. All right. So what we're going to do now is I'm going to give a flag style derivation that shows that the formula that you see now here on the slide. Let me copy it and then I'll show you my my virtual blackboard. So for all, and there exists x for all y. Py implies q, y, x. If that is true, then for all x, px colon exists y, q, x, y. So we're going to derive we're going to prove with the derivation that this formula is a tautology. Let me show you my blackboard so that you can see what we're going to do. Now let's remember immediately this advice that I gave you to actually make sure that bound variables are named differently in the various parts of the formula. And as you may notice, if you look at the formula, this exists x, and there's also the universal quantification over x. And note that this x and this x, well, the scope of this x actually ends here, right? So this x is bound to only this x over there, and it has nothing to do with the x over here. And that may lead to confusion in derivation. So what we are going to do is rename the bound variable, the second bound variable x, to something else. Let's call it z. So we are going to rename this. Maybe that color is not the best color, the most visible color. Let me see whether I can find something lighter than that. So what we are going to do is we're going to call this, let's call it a z. And then, of course, we should do that consistently. So also this x should become a z, and also this x should become a z. And now we can make a similar observation about the universal quantifier here. So this has something to do with the y that you see over there, and also with the y that you see over there, but it has nothing to do with the y that occurs here. So let's also rename that one. Let's call that one u, and that one 2. Right, so you may also always do this this renaming. So already when you copy, for instance, the formula on your sheet of paper, actually I have the habit of already doing it for you when I pose test questions. But you have to realize also when you do the exercises from the book that that you have to be aware that this is something you have to take into account. You have to. It's always better to make sure that bound variables are named differently in the various for the various quantifiers. So now we have an exists x for all y, for all z exists u. Okay, all right. So let's now start to make actually the derivation that we're looking for. So we want to prove that this formula is a tautology. And how do we make derivations? Well, we always start with looking for the main symbol. In this case, that is actually an implication. So we do implication introduction the assumption is going to appear on line 1, and then there will be some. I mean, the goal will, we don't know yet at which line that will appear. So here we get an assumption on the top of our sheet. And the assumption will state exists x for all y, py implies qy x. And we put that in a flag. There we are. And so then our goal becomes to prove for all z, and mind you, we have renamed the variable. So for all z, pz exists u, q, z, u. Okay, let me check the chat because there was a question coming in. So the question is, do you need to explicitly specify the renaming step of the bound variables? And the answer is no. You may do this implicitly, and that means that you could have already renamed the variables when you actually copied the formula to prove on your piece of paper. So renaming bound variables may be done implicitly in derivations, but this only pertains to bound variables. So when it's attached to a universal quantifier or an existential quantifier, and it doesn't pertain to all variables. All right, let me now see whether I can actually manage to get also, no, this I don't have the rules here. So now what we are going to do is maybe you want to grab a copy of your book and actually also look up the rules for universal quantification, introduction, elimination, and similarly for existential quantification, elimination. I cannot show them to you here. If you remember, the universal quantification introduction rule allows us to prove a universal quantification. So here we have a formula that is of the shape for all z something. And then the universal quantification introduction rule says, okay, then you declare an arbitrary element z, assume that it satisfies the domain predicate, and then the goal will be to prove that it satisfies the predicate after the colon. So that's that will be an application of for all introduction. So we apply universal quantification introduction on, so this will be line 1, and this will be on line 2. The assumption will be on line 2, or the declaration of the variable, and we don't know yet what will be at which line number our goal will actually appear. But here we have another assumption, and so we now declare an arbitrary thing z and assume that it satisfies the domain predicate p of the universal quantification, right? And we put that in a flag because, again, this is, well, we basically insert an object into the context, an arbitrary object of which we only assume that it is in the domain of the universal quantification. And now our goal becomes, that is a very ugly flagpole. Let's try to do that better. Our goal now becomes to prove that there exists a U such that Q Z U holds. Okay, now if you remember the rule for existential quantification introduction, it says, okay, what you need to do to prove an existential quantification is you have to find a witness. So you want to find some object in your derivation satisfying this predicate Q, QZ, I mean, the object in the existential quantification is called U, but it doesn't have to be called U. The object that you need to find, the witness, doesn't have to be called U. It can be something else, but it has to satisfy this predicate. Okay. Now, at this point, it's still unclear what actually is the suitable name for the suitable object. We don't have it yet. So we leave we leave this for now, and we're going to check what we see over here. By the way, and maybe you were not. Maybe I should have said this before, but so there's something else that we have here with this existential quantification. You may wonder where did the domain go? Well, we have adopted the convention that we omit the domain true to simplify the existential quantification, but you should think of it as if the domain true is actually added to this existential quantification, and the same holds for actually the universal quantification over there. So also there, the domain true has been omitted to make it I mean, it's a sort of abbreviation that was introduced previously, and also that sort of happens here. Here we have the existential quantification. The domain of this existential quantification is true, and this is the predicate of the existential quantification. So we have used a couple of abbreviations that are common and that have been introduced. You may have a look at the slides about predicate logic where this is explained. All right. Now, the first thing we can do with what we see here at the top of our derivation is we can actually eliminate the existential quantification over here. We know that there exists an X satisfying this predicate, and so we may declare a witness for this existential quantification. So let's do that. Let's do that in white. And let's first put the line number here. So what we are going to do is we are going to apply this exists star elimination rule on line 1. And that will result in the declaration of some X satisfying the domain predicate of the existential quantification. But here, as you can see, the domain predicate is true, so it doesn't really, well, let's write it for completeness sake, but you can omit it if you want. So we pick an X such that, it satisfies true. This part can be omitted, and it satisfies the universal quantification. For all y py implies qyx. It's still visible, barely, but I think you can still read it. So what we have done is we have eliminated the existential quantification in a way by saying, okay, there has to exist a witness, and we don't know what this X is, but we can use this X in our proof. And it satisfies true, and also that's the domain predicate, and it also satisfies the predicate, the universal quantification. So now let's try to use this universal quantification. And what is a good way to, how can we use it? Well, if we have an object in the domain of this universal quantification, and now you have to remember that actually the domain of the universal quantification has been omitted because it's true. Well, every object satisfies the domain predicate true, so there's no real requirement on the object that we need here. But if we have an object, then we can eliminate the universal quantification. And there's only one object. Well, there's actually two objects that could do the job here. We could use this object here. It has been declared, so we can use it to do universal quantification elimination. Or we can use this object, which has also been declared. Now the question is, what is the most useful object to use? And then it's maybe good to look ahead at what we're actually aiming for. We want to get something of the shape QZU. We want to apparently have this Z, and that's also this Z, at this position in the existential in the Q predicate, right? So there's a Y here. That's actually the universally quantified thing. So let us do the universal quantification elimination using Z. So we do for all elimination, and we do it on line 3. Line 3, there you find the universal quantification. That's this one. But it's always important to also mention the object or actually the place where it is actually proved that there is an object satisfying the domain predicate. Now, in this case, the domain predicate is trivial, it is true, but still it would be good to refer to the object in line 2, because that's actually the one that we're going to use for the elimination. So let's mention here that we do universal quantification elimination on 3 and 2. And that yields, and now you should be careful, now what we do is we replace the Y, well, this Y and this Y by this object, right? So we get PZ implies QZ X, all right? And now we can continue. So this is line 4. Now we can continue because we have an implication. And if you remember, the rule for implication elimination states that if you know an implication and you have its left-hand side, and we have it over there, then we can actually conclude its right-hand side. So now we can conclude with implication elimination on line 4, and also, so that's where the implication is, and on line 2, that's where actually the left-hand side of the implication is, we can conclude Q, Z, X. All right, and now we're almost done, because the last thing we still need to do is to actually realize that if we that we now have proved that the predicate Q holds for Z and X. Okay, and what did we need to prove? What was our goal? To prove that there exists some U satisfying the predicate Q with Z. Okay, and now so now we have basically our witness. We have this object X. It has been declared over there, and this object indeed satisfies the properties that we need for U. So we can do existential quantification introduction on, well, 5, and you may want to mention that but you may omit it, and true, because you always so the domain specification of the existential quantification is true, but you don't have to specify it because it's trivial. Every object satisfies true. And now our derivation is complete. Let me check. There are a couple of questions. So wouldn't it be smart to name the x on line 3 some other letter, is the question. So you're referring to this x over here. Well, you have to give it a name that does not yet occur. And you could say, okay, but I see it over there. But when we are talking about occurrences of variables, we ignore basically the bound variables. So it is if you have done the thing that I've done in the beginning, it's always so if you make sure that the bound variables are named differently, then you can always here take this. Then you can always take here the same variable name as you used for the existential quantification. So, but it is not. So it is correct to actually invent a new name there if you're worried about that. And then there's another question. Another question is, why don't you name it U? That is also a valid choice at this place. You could also name it U. Also for the same reason, the U does not yet occur on this. If you look at this at the place of this derivation, the U does not yet occur, and then in a way you could say then here you would get the U, but it's not. There's no real need to do so because the existential quantification introduction that you do there actually doesn't require that you have a U over there. So you can do it. It's valid, but I don't see a reason why you would do it. All right, question. What I don't get in this reasoning is that you can introduce a universal quantification by proving that there is one variable that satisfies both domain and predicate. How does that prove that the entire domain yields true from the predicate? Okay, so this is about the validity of universal quantification introduction. We are trying to prove this universal quantification here. And the question is, okay, how could you conclude this universal quantification if you basically prove it actually for only one thing, namely the z that you declare over there, right? And that's a very valid question. The point is, this z, you don't assume anything about it. So the only thing you assume about it is that it satisfies the domain predicate of the universal quantification. And that means that what you're actually giving here is a sort of general proof that no matter what you would take for z, actually you get a so suppose that p is the predicate, z is an integer, right? So basically what we want to show here is for all integers some predicate holds. Now what this proof here says is that if you have an arbitrary integer, say 3 or 4 or 10 or 365, then this whole proof you can instantiate with this particular integer and it will still be valid. And that's the power of actually declaring something arbitrary here. So you say basically this is all sometimes referred to as generalization. So you give a general proof of this predicate for a general thing that doesn't really depend on anything else than being in the domain. All right, that is how you can think about it. But the formalities are formally basically you just declare a new thing, a variable of which you assume only that it is that it satisfies the domain predicate. And then there's a question: do you need still valid? Well, I didn't need it in this proof. I'm not sure why where you would like to see it. Still valid is used when actually you apply an introduction rule typically, and basically with the introduction rule comes the formulation of a new goal, and then you look in your derivation and you see, hey, but the new goal that I need to establish is already there. So so there's nothing to prove really because this formula that I need to establish is still valid, and that is the only reason to actually use still valid. Okay, and then there's still a question: what does the true in line 3 represent? So you mean, I suppose, this true? Yeah. For that you have to look at the rule for existential quantification, elimination and introduction. Let me try to show you my slides there. Let's see. So let me show it. Unfortunately I cannot show you both at the same time, but I can show you the slides. So if you notice here, this is the rule for existential quantification introduction. So it says you have to declare an element, and this element should satisfy both Px. Well, I mean that means that this is the domain of the existential quantification, and it should satisfy Q. That is the predicate that you're trying to prove. Now the point is, and I'll switch back to the blackboard now. The point is that that actually this, if I manage. The point is actually that this Px and I'll show you the blackboard in a bit. The Px is actually true in the case that we are applying it here. So the this true here refers to the domain of the existential quantification. All right. I think so. This concludes the presentation of this example. There is one thing that I still want to point out regarding the derivations with quantifiers. For that, I have to move I have to show you some other slides. Let me do it like this. So let me show you one. I want to show you a full question. And I'm sorry that I have to scroll first through these things. Oops. All right. Well, that went a bit too fast maybe, but I have this this poll question pertaining to existential quantification still for you. You can go to Mentimeter and enter your answer there. Let me check whether the question is already enabled, because otherwise you cannot do anything. No, probably not. But now it is. So question, look at these formulas. There exists an integer x satisfying p, and there exists an integer x satisfying q. Suppose that these formulas are both valid. Can you then conclude that there exists an integer x satisfying both p and q? I'll give you 1 minute to think about it. Please enter your answer in Mentimeter. All right, let me check. I cannot at the moment see the status of the Mentimeter. Mentimeter. Let me. Oh, I'm sorry about this, guys. I should have paid attention. You can vote now. So let me show you again the question. At least you had some time to think about this question while you couldn't enter your vote. And let me give you half a minute to enter your vote. Okay, I propose to have a look at what is the situation in Mentimeter. At least also 152 students already have entered their answer. Let me show you the results. Most of you say no, this is not something you can conclude. A couple of you say yes, and one of you says, I don't know. The answer is indeed no. The majority is right again in this particular case. Let's see the answer. I actually showed it already to you, or let's explain the answer. So just to give you a counterexample to this statement. So suppose that we are considering two existential quantifications. There exists an integer x satisfying x less than -5, and there exists an integer x satisfying x is greater than 5. Now both existential quantifications are of course true, because there is an integer less than -5, and there exists also an integer greater than 5. But certainly there does not exist an integer x that is both less than 5 and also greater than 5. And this is to point out to you that, and you will notice that is at some point when you're doing these exercises and doing existential quantification eliminations, especially later in the course when we're going to apply these things to set theory, you're going to notice that sometimes it is tempting to use the same variable twice when you declare witnesses for separate existential quantifiers. And that is not valid. I mean, this is why you should choose, if you eliminate, say, this existential quantification first, then you can still choose an x. But if you then also want to eliminate, oh, that is not what was supposed to happen. If you then also want to eliminate this existential quantifier, then you should not again choose x, because then basically you get a witness that would satisfy both x less than -5 and x greater than 5. All right. Perhaps this is still a bit abstract. I'll refer to this back to this problem later in the course when we're going to discuss, well, for instance, divisibility. That in those contexts this happens easily. All right. Now let me. I think I would like to now close the subject. Well, no, there were a couple of questions still in the chat that are worth addressing. So let me move back to the Blackboard. And so one of the questions that appeared in the Canvas chat is the following. So how do you go from QZX to QZU? So that is this one. How do you go from here to well, I mean, so to here, I think. So the point is there is no QZU. So there is an existential quantification, right? There is a formula that says exists U QZU. There doesn't. So we're not going from QZX to QZU. We're going from QZX to there exists a U QZU, right? That's a very important difference. And so how do we go there? Well, we apply existential quantification introduction. I'll show you the rule in a bit. But the idea is, if you want to prove an existential quantification, then what you do is you find a witness, and we have found the witness here. It's called X. The X is the witness for the existential quantification introduction, or for this existential quantification, and therefore we can now conclude that we have proved it. I'll show you the rule in a bit well, I mean, there was another question that maybe I should address. So another question was, shouldn't it be existential quantification elimination instead of introduction? And the answer is no, because existential quantification elimination is when you reason from top to bottom. So here we have an application of existential quantification elimination. We know an existential quantification, and we apply the elimination rule to basically eliminate this one, going from top to bottom, and declare a witness. What we have here is an introduction. We know that that the predicate Q is satisfied for Z and a particular witness, and then we conclude the existential quantification. Just to show you, let me just show you the rule once more to make sure that that it's clear what we're talking about. I'll show it in a bit. Let me first put the right slides on again. That should be there. And now I'm going to show you the rules. So So elimination is this. So you know an existential quantification and you reason from top to bottom and then you declare a witness. An existential quantification introduction, that was this rule. So you want to prove an existential quantification, right? That's on the bottom, at the bottom of the rule. So this is what you want to prove. And the existential quantification introduction rule says, okay, then it's enough to find a witness. And here the witness is called A. In our proof, our example proof, it was called X. Okay. Is there a formal way to state line 3 is still a question. Let me move back to the blackboard. And this is the there are now still 2 questions that we'll address. So first of all, is there a formal way to state the thing in line 3? Well, this is the formal way to state to declare this witness. And why is it formal? Well, because the book actually has promoted this statement to a rule. And I fully understand why you don't think it is formal, because it says it has all sorts of text in it. But the fact that it has text not necessarily makes it less formal. We always use this scheme to write it. So we always write pick an X such that, and then we get the predicates. Okay. So although I can imagine, I understand why you find it somewhat informal, because we always do it like this and never otherwise. It is formal in that sense. Then another question: is a witness a bound variable? And that is never the case. So what are the bound variables here? So there are a couple of bound variables in this proof. This will be the last thing I'll do. Let me mark the bound variables. Let me see. Let me try to do that here. So let me mark them in yellow. So, or blue. Why not blue? So this is a bound variable, and this one is an occurrence of a bound variable. So all these things are bound variables. What is not a bound variable is, and there are many more, like here and here and here. Is this visible? I think so. This, there. All these things are bound variables. As soon as you have a quantifier, and it's bound by a quantifier. This is how you should say it. What is not a bound variable is, for instance, this z over here. That is not a bound variable. It is a declared variable here. It's as well, in this part of the proof, it occurs free, right? And also here, this z here is free. This z and this x are both free. Because they are actually, but as if we go to this existential quantifier, then again this u is bound. Okay, hope this clarifies it. All right, let me see. I propose to have a rather short break now, and then the last hour we'll talk about set theory. Let's have a break, say until what is it? What time is it now? Until 16:35. So we reconvene at 16:35, and then we'll continue with the lecture and talk about set theory. Lecture continues at 16:35. All right, see you in 10 minutes. All right, ladies and gentlemen, before we continue, let me test one of the setups. Oh, that goes reasonably well. All right. Okay, so this concludes our discussion of derivations. We have started to discuss derivations because we wanted to formalize the idea of a proof, and wanted to formalize the way in which mathematicians reason when they are proving a mathematical theorem. What we're now going to do, basically the remainder of the course, we are going to use this, basically we have now created a toolbox with reasoning methods, and we're going to use this toolbox to prove all sorts of statements about sets and functions and relations, and towards the end of the course also we're going to introduce induction. So the idea is we're now going to basically apply the logic that we have learned, and we are going to apply it first to set theory. And I want to start with another video that introduces, that gently introduces, I would say, the notion of set to you. And then I'll come back with a quiz question about what you've seen. And I'll start another video, and after that I'll do another example also on my iPad. Okay, so first, please have a look at and watch the video that introduces sets and how to reason about them.
In the remainder of this course, we shall use the logic that has been treated extensively in the preceding lectures to precisely define and discuss other mathematical topics. And we start now with the notion of set. Everybody probably has an idea of what is a set. Perhaps the first thing you think of is the scoring system in tennis, where a set is a bunch of games. Or perhaps you think of a cookware set, a bunch of tools that allows you to cook. Intuitively, a set is a collection of things of the same type. So, for instance, a box of chocolates can be considered to be a set. And here you see a picture of a stamp collection, or perhaps of a set of stamp collections. You have probably also already encountered the notion of a set in a mathematical context. Let us consider some examples. If the natural numbers 0, 1, 2 and 3 are grouped together, then they form a set of numbers. We use curly brackets to actually form the set. The notation is important and has a meaning. It makes explicit that we intend to group the numbers. But also it tells us that we do not care about the order in which the numbers are listed, nor about their multiplicity. So, the set containing the numbers 0, 1, 2 and 3 is equal to the set containing the numbers 3, 1, 0 and 2. And it's not important whether we list the numbers appearing in the set more than once. The only thing that matters is whether the number occurs in the set or not. Sets are allowed to be infinite. I'm sure you are familiar with the following symbols denoting certain infinite sets of numbers. The symbol n is often used to denote the set of all natural numbers. Please note that in this course we adopt the convention that 0 is a natural number too. Similarly, we have the symbols z and r denoting the sets of integers and real numbers, respectively. We introduce a binary predicate denoted by the Greek letter epsilon to express that something t is an element of the set x. Now, if we take concrete values for t and x, then we get a proposition. For instance, we get a true proposition by taking 1 for t and the set consisting of the numbers 0, 1, 2 and 3 for x. We pronounce the obtained proposition as 1 is an element of the set consisting of the numbers 0, 1, 2 and 3. We get a false proposition by taking 4 for t instead. 4 is not an element of the set consisting of the numbers 0, 1, 2 and 3. That something is not an element of some set is often denoted with a crossed out epsilon. Listing the elements of a set between curly brackets works fine for small sets, but for large or infinite sets it's very impractical. So we now introduce a more sophisticated method to specify the elements of a set. Suppose we have a set X and a predicate that expresses a property of the elements of X, a property that elements of X may have or may not have. Then we use the following notation to specify the set of all elements of set X that satisfies the predicate P. Thus, we can now specify the set of natural numbers greater than 10. And the set of integers x satisfying x squared plus x is less or equal 0. The intuitive interpretation of the set specification mechanism is made precise with the following property of the element of predicate. Consider the predicate T is an element of the set of all elements in X satisfying the predicate P. The property of element of states that this predicate is logically equivalent to the predicates T is an element of X and T satisfies P. This property of element of, formulated here, should not be regarded as a property that can be proved. It should be regarded as an axiom of set theory. It defines the interplay between the element of predicate and the set specification mechanism. We shall use this and other properties later to prove statements about sets. We now have a mechanism to specify complicated sets using predicates. But you may have already observed that in order to use the mechanism, we should have a set, X, that contains at least all those elements that we would like to put in the new set. So it would be nice to have some kind of absolute universe that contains everything that we would ever like to put in any set. However, as Russell's paradox shows, such a universe, such an absolute universe, cannot exist. It's logically impossible. Russell's paradox is outside the scope of this course, but on the internet you'll easily find good explanations of the paradox. For the purpose of this course, it is still convenient to refer to a relative universe. The symbol U will denote, in a certain context, the set of all relevant things, numbers, sets, etc. The symbol U is characterized by the property that states that everything T is an element of the universe. Again, let me emphasize that the universe is relative to the context. It is a convenient logical tool, but does not have an absolute mathematical interpretation. We proceed to define and discuss another important predicate pertaining to sets, set theoretic equality. We say that two sets are equal if they have exactly the same elements. So for instance, the set containing the numbers 0, 1, 2 and 3 is equal to the set containing the numbers 3, 1, 0 and 2. Remember, the order of the elements does not matter for a set. Also, the set of all integers greater than 0 is equal to the set of all natural numbers not equal to 0. And the set of all integers satisfying the predicate x squared plus x is less or equal 0 consists of the numbers minus 1 and 0, because minus 1 and 0 are the only integers that satisfy the predicate. We define the equality predicate on sets A and B with a formula that expresses that A and B have the same elements. The predicate A is equal to B is logically equivalent to the formula stating that every element of the relative universe is an element of A if and only if it is an element of B. Note how the formula defines the equality predicate on sets in terms of the more primitive element of predicate. You may also note that the domain of the universal quantification is true by the property of relative universe. For this reason, the domain specification stating that X is an element of the relative universe is often omitted from the universal quantification. We introduce a symbol to denote the unique set without elements, the empty set. The empty set can be defined as follows. It is the set of all elements in the universe satisfying the predicate false. Let's formulate some standard properties involving the notion of empty set. The predicate T is an element of the empty set is logically equivalent to false. The predicate A is equal to the empty set is logically equivalent to the formula for all x in A, false. Both properties can be derived from the definitions of empty set and equality on sets using the property of element of and standard logical reasoning. The mathematical theory of sets does not start with a precise definition of what is a set, as you might have expected. This has to do with Russell's paradox, which states, or which has as a consequence, that there is no absolute universe of all sets. Instead, we have introduced symbols denoting special sets, and we have introduced two binary predicates on sets, and we have introduced a mechanism to specify sets using predicates. We have, for instance, used this latter mechanism to define the empty set. This concludes our introductory lecture on sets. In the next lecture, we will discuss operations on sets.
Okay, that was an introductory video on sets. I'd like now to do one quiz question, and now the big question is, will this work? I was a bit worried about that. Indeed, this screen would be a bit too small. Let me make it a bit bigger for you. So then I have to do it like this. All right. The question is, the goal is to select all sets. What you see here is 6 expressions. The question is, which actually denote sets? Please enter your answers in Mentimeter. Okay, I'll give you half a minute. Aha. So I now my colleague now says that that I configured this question incorrectly by not giving you the option to actually select all sets. That is very unfortunate. Then there's nothing else to it. I'm afraid we cannot repair this right now. We'll discuss it in a bit. Perhaps, well, hopefully you selected your favorite set then. Let me immediately show you the answers then, because it does not make sense to let you enter just one answer. First, let me show you the result. Apparently, the most preferred set was the one listed for A. Indeed, that is a set. Let's go through the other examples. So A is indeed a set. So you can specify a set by writing curly braces, and mind you, this is special notation. So you cannot use other kinds of parentheses or brackets. It has to be the curly braces, and then you can list the elements of the set. So the answer for A actually lists or specifies a set that has 3 elements, namely the numbers 3, 4, and 5. Then the answer B is not a set, because the number 3 without the curly braces just indicates, of course, a number. There's no set specified there. Then B is not correct. It's not a set. Then let's have a look at C. There we use a special way of specifying sets. We can specify a set by using the curly braces notation. And then, list basically saying on the left-hand side of the bar, we specify a domain. We say, okay, we consider all elements x of the set of integers. And then on the right-hand side of the bar, there has to be a predicate. So, and this predicate specifies that basically that this x has to be a multiple of 5. Right? So this, as you can see on the right-hand side of the bar, we have specified a unary predicate. It has a free variable x. It has also a bound variable y. And basically expresses that x should be a multiple of 5. So C is also a set. Then D, you may argue about that one, but we allow this kind of notation. The set containing the elements 3, 5, 4, and 3 is mentioned twice more. What is important to realize that the set specified for A and the set specified for D are the same. They are considered to be equal. The idea is you list the elements of the set between curly braces, and it only matters whether an element is in the set or not. If you list it twice, that doesn't add anything special to the set. Then for E, Well, that it may look like something similar to C, but here there's a problem, a sort of syntax error, you could say, because there we have a real number. X is an element of the real number, so that's on the left-hand side of the bar. It's okay, but on the right-hand side it says, well, something like pi times x. Well, pi times x is not a predicate; it's a number. So if you take a real number, then you can multiply it by pi and you get again a real number, but you don't get a predicate. You don't get true or false. So E is not specifying correctly specifying a set. And finally, F is again a set. So we use this crossed out zero to denote the empty set, the unique empty set. And please use this notation instead of opening curly braces, closing curly braces. That is not the notation we're going to use for the empty set. All right. I want to show you one last video which introduces all sorts of operations on sets. And after that, we're going to see a couple of proofs in the context of set theory. There we go.
In this lecture, we will discuss definitions and properties of set theoretic operations, intersection, union, complement, and difference. Let's start with intersection. To explain what is the intersection of two sets, we use a so-called Venn diagram. It shows the universe, and it shows two sets, A and B, and now the intersection of A and B will be the part at which they overlap. Intersection is more formally defined as follows. A intersection B is the set of all elements that are both in A and in B. To give an example, the intersection of the set of natural numbers greater than 5 and the set of natural numbers less than 10 is the set consisting of the natural numbers 6, 7, 8, and 9. From the definition of intersection and the property of element of, we can derive the following property of intersection. The predicate stating that something T is an element of the intersection of sets A and B is logically equivalent to the predicate stating that T is in A and T is in B. The union of sets A and B consists of the elements that are either in A or in B or in both. Formally, the union of A and B is defined as the set of all elements that are either in A or in B. Recall that disjunction is inclusive. Here's an example. The union of the set of natural numbers greater than 5 and the set of natural numbers less than 10 is simply the set of all natural numbers. From the definition of union and the property of element of, we can derive the following property of union. The predicate stating that something T is an element of the union of sets A and B is logically equivalent to the predicate stating that T is in A or T is in B. Consider the set A part of the relative universe U. The complement of A, denoted by A with a superscript C, consists of the set of all elements that are in the universe but not in A. Formally, the complement of A is defined as the set of all elements in the relative universe that are not in A. We give a few examples. The complement of the set of integers greater or equal to 0 is the set of integers less than 0. This is under the assumption that the integers form the relative universe with respect to which we want to take the complement. It is important to know the intended relative universe for computing the complement of some set. Consider the set consisting of the numbers 0 and 1. If we want to compute its complement, then we need to know what is the intended relative universe. If the relative universe is the set of natural numbers, then the complement of the set containing the numbers 0 and 1 consists of all natural numbers greater or equal to. If, however, the relative universe is the set of integers, then the complement of the set containing the numbers 0 and 1 consists of all integers that are either negative or greater or equal to. From the definition of complement and the property of element of, we can derive the following property of complement. The predicate stating that something T is an element of the complement of the set A is logically equivalent to the predicate stating that T is not an element of A. The difference of a set A and a set B is the set of all elements that are in A but not also in B. Formally, the difference of A and B is defined as the set of all elements that are in A but not in B. Here's an example. The difference of the set of natural numbers greater than 5 and the set of natural numbers less than 10 is simply the set of all natural numbers greater or equal 10. From the definition of difference and the property of element of, we can derive the following property of difference. The predicate stating that something, T, is an element of the difference of sets A and B is logically equivalent to the predicate stating that T is in A and T is not in B. We have presented 4 operations on sets: intersection, union, complement, and difference. And we have defined these operations using the mechanism for specifying sets and predicate logic. And from these definitions, we have also derived a property for each operation that will be useful in reasoning about these operations later. This concludes our introduction of 4 operations on sets. In the next couple of lectures, we will discuss a technique for proving the equality of sets and for refuting the equality of 2 sets.
Okay. You've seen the introduction of a couple of operations on sets. So if you have 2 sets, then you can take their intersection or their union or their difference, or if you have a set, then you can take its complement. And what you should have seen in the video is that the complement of a set is always with respect to some presupposed universe. And in this course, let us agree that that we should, if we take the complement, then we should always specify which universe we are actually taking the complement. I mean, what is the relative universe with respect to which we take the complement of a set? Now let's discuss a couple of definitions still. Let me keep myself in the slide. So basically we are going to illustrate the use of these operations, intersection and union, by considering a property. So if you have 3 sets A, B, and C, is it always the case that A intersected with B and then after taking the intersection, take the union with C is the same, is equal? Is equal in terms of set theory to the set that you get by taking the intersection of A with the union of B and C. Okay, so what we want here is one of 2 things. Either we want to prove this statement, and then we give a formal proof in terms of the properties and definitions pertaining to set theory that you have seen, or we should provide a counterexample. We should provide concrete examples of sets A, B, and C that refute this equality. Now let's think about it first in terms of pictures. That usually helps to investigate what is actually the case here. But please remember that the picture itself is not a proof nor a counterexample. So after having formed an opinion on the basis of pictures, we still always have to either provide a formal proof or provide a concrete counterexample. Now, for this particular example, still you might say that the pictures are convincing, but we'll see later that pictures do not do the job anymore. Let's first draw the picture. So let's first construct this. Here we have a sort of most general representation of the 3 sets A, B, and C. They may actually have some overlap between themselves, and also have parts that do not overlap. These pictures are called Venn diagrams typically. And now we can sort of carve out the area that is denoted by the set by A intersection B union C. So let's first compute the intersection. So the intersection of A and B is the part that they have in common. And then if we take the union with C, then we get the purple area. All right. So that is A intersection B union C. Let's also compute or illustrate what the other side of the equality looks like. So then we start with computing the union of B and C. That is taking the areas demarcated by B and C together. And then we want to take the intersection with A, which means that we throw out everything that is not also in A. So we get this set. Now, what you can see from the picture already is that these two sets are not equal. The purple area in the left Venn diagram is much bigger than the purple area in the right Venn diagram. So let's now try to provide a concrete counterexample that refutes the statement, that refutes that these two sets are equal, and prove in this way by means of a counterexample that the statement does not hold. How does that work? Well, we should declare sets A, B, and C concretely, and for instance, put some objects in those sets, and then use the definitions of intersection and union to compute the results and see that they are not equal. So there we go. So first of all, it helps to associate with every area a number. So you can imagine now that we will let the set A consist of the numbers 1, 2, 5, and 4. And the set B will consist of the numbers, will contain the numbers 2, 3, 5, and 6. And the set C will contain the numbers 4, 5, 6, and 7. And we also put, just for the sake of completeness, a number in the area outside A, B, and C. So, and the same thing we do on the right-hand side. Basically, we put a number in every separate area. And then we can basically read off the counterexample. So we can say, okay, let now A be the set consisting of the numbers 1, 2, 4, and 5. And let B be the set consisting of the numbers 2, 3, 5, and 6. And finally, let C be the number consisting of the numbers 4, 5, 6, and 7. Then what will be the intersection of A and B? Well, that's everything that is both in A and in B. So that's the set containing numbers 2 and 5. Okay. And what is the set that you get by taking the union with C of the set containing numbers 2 and 5? Well, then we should add to the set 2 and 5 everything that is also in C. So that's the numbers 4, 5, 6, and 7, right? So we get the set 2, 4, 5, 6, and 7. There we have computed the intersection of A and B united with C. And now let's let's also compute the union of B and C. Then we get the set that contains everything that is both in B and in C. So that is basically the numbers that you see over here and the numbers that you see over here. So 2, 3, 4, 5, 6, 7. And now if we take the intersection with A, then basically we discard everything except the numbers that are also in A, and that is 2, 4, 5. Right. So now we have a concrete set. That is the intersection actually of A with the union of B and C. And now it's a matter of observing actually that these two sets are not equal. So first of all, we have the set A intersected with B and then taking the union with C. Now, why are these two sets not equal? And now you have to be careful. They are not equal because there are elements in this set that are not also in this set. Remember, two sets are equal if all the elements in the first set are also elements of the second set and the other way around. Now, because the number 6, for instance, is in the left-hand side set but not in the right-hand side set, we can conclude, okay, these two sets are not equal. The left-hand side is equal to the left-hand side expression, A intersected with B union C, and the right-hand side set is equal to the right-hand side of the equality, A intersected with the union of B and C. Okay, so, and this is the counterexample. Here with this concrete instantiation of A, B, and C, we refute the equality. Okay, now you may observe something here before I get to the next slide. You may observe that there is another relationship that exists between these two sets. So if you look at the area that is purple in the right-hand side Venn diagram, then you may observe that it actually that all the elements that are in the purple area in the right-hand side are also in the purple area in the left-hand side. So so they are not equal, but there seems to be some kind of relationship still, and this relationship is called inclusion. And let's give a definition of that. There's also a video about that, but I'm not going to show that today. I'm just giving you the definition here. So we say that A is a subset of B, and we write that this is the symbol that we are going to use for inclusion. If every element of A is also an element of B, but not necessarily the other way around. So that is the definition of inclusion, and that is the sort of informal definition of inclusion. Let's cast this in terms of predicate logic. So the expression or the predicate A is a subset of B is defined as for all x an element of A, we have that x is an element of B. So note that we are defining here a new symbol, intersection, in terms of symbols that have a symbol that is already defined, namely element of. You have already seen the notion of element of appearing in the video. And so we use quantifiers and predicates to actually express what it means to say that A is a subset of B. For all elements in A, there are also elements in B. All right. And now there's an important property of inclusion that you can use in proofs, and that is formulated in the shape of this logical consequence. If you know that A is included in B, and you have a particular element that is called T in this rule of the set A, then you may conclude from that. So a logical consequence of that of that conjunction of those two premises, you could say, is that this element T must also be an element of B, right? So if you know that A is a subset of B, and you happen to have an element of A, then you may conclude that it's also an element of B. All right. Let's move back to the example, and let's now actually and now we can formulate a conjecture, namely that that we have an inclusion here always for all sets A, B, and C. And so let's prove by means of predicate logic now that A intersected with B union C is always a subset of the union of the intersection of A and B and the set C. So that's what we're going to do now. Let me move to my blackboard, and there I have already written the inclusion that I want to prove, and that's what I'm going to do now. And I think I have a way of showing you actually, so now and then, a couple of rules, a couple of properties that we are going to use. Let me see whether that actually works. Not exactly as I had hoped, but let's repair this a bit. So unfortunately, I have to sort of resize this thing like this. Somehow in the break at some point I thought let's look something up on my iPad, but then I realized that actually my iPad screen was streamed, so that went hopefully wrong. But now it's, I think, better. We can see both the proof and you can also see the slide with a couple of definitions. So there we go. We want to establish, in the meantime, we want to establish an inclusion. And from the from the definition of inclusion, that's on the top left of the slide. I think I can point it. I can point it here. So that is this definition here. By the definition of inclusion, let me write it like this. It suffices to prove that for all x, if x is in the left-hand side set, say in the set A intersected with the union of B and C, then x is an element of the right-hand side set. So in the union of the intersection of A and B, in the union of the intersection of A and B and C. Okay, so now we have basically reduced this predicate to a statement to which we can apply the rules that we have learned. The rules that we have learned in the first part of the lecture. We can do a universal quantification introduction on this formula. Let's put the sum that it will give us an assumption on line 1. And the assumption will read, so there we go. The assumption will consist of the declaration actually of a variable x, and of this variable it is assumed that it is in this set in the intersection of A and the union of B and C. Okay, so this is our this is a flag, and in the context of this declaration, we now need to prove that X is actually an element of the union of two sets, namely on the one hand the intersection of A and B, and on the other hand C. Okay, and now we can continue with reasoning about the thing that we see over here. What we now need to prove is that X is actually an element of some union. And if you look on the at the properties that we've specified here, so when is something an element of the union of two sets? So that's the rule at the bottom right. Something is an element of a union if we have that this thing is either an element of the left-hand side of the union or of the right-hand side of the union. So we reduce it now to a disjunction. So, oops, wrong pencil. Let me. So now we apply the property of union, which says that it's now enough to prove that X is an element of the intersection. No need for the parentheses. The intersection of A and B, or X is an element of C. Okay. How do you prove a disjunction? Well, there are two rules for proving a disjunction. One is to assume the negation of the left-hand side and prove the right-hand side. And the other is to assume the negation of the right-hand side and prove the left-hand side. And we don't know beforehand what is the best approach. So before we get to do that, let's first figure out what we actually know. And I now see that I made a terrible mistake here. So let's repair that immediately, because I write something that doesn't make sense at all. What I wrote here is a set instead of a predicate. So let's remove this immediately. What I should have said is I should have written a predicate X is an element of A intersected with the union of B and C. Now it is a bit better. I think it's now actually correct. All right. Oops. So very important, and this is a mistake that we see students make a lot in the beginning. So note that the elements of a derivation, what you have on a derivation, in a derivation, everything here should be a formula, a predicate. So it cannot be a set. So so it would be very strange to write a set here instead of a predicate. We need something of the shape X is an element of this thing. Maybe actually by making the mistake myself now, I have prevented that you are going to make it. So if that is actually the effect, then this is nice. Let's continue. So we can now we now know we're going to reason about this predicate here. So X is an element of the intersection of two sets, and if you look at the rule on the right in the middle, then you can see that this being an element of an intersection means that that this element is an element of both sets. So this is by actually an application of the property of intersection. We get that X is an element of A, and we get a conjunction, and X is an element of the union of B and C. Okay. All right. Well, we can now continue still a bit reasoning about this expression over here, because now if we know that we can first apply a conjunction elimination. Let's do that first. Conjunction elimination. Let's also start to write some line numbers. Conjunction elimination on line 2. To get actually X is an element of the union of B and C, and that is convenient because now we can continue with our reasoning. We can apply the property of union again, which says that And note that if you look at the property of union on the bottom right, then we have an equivalence here. That means that we can apply this, and an equivalence is basically a logical consequence in two directions. So we can, from the left-hand side, conclude the right-hand side, and that is actually what we're going to do now. Previously, actually, you could say that we have applied the logical consequence in the other direction. That was actually over here. Here you could say, okay, we go from the disjunction to the union. All right. So we can conclude now that X is an element of B or X is an element of C. Okay. Now let's consider what we need to establish here. We want to prove that that actually X is an element in the intersection of A and B, or X is an element of C. Now, and now we have more information to know which disjunction introduction rule we could apply. Note that if we take the negation of this thing over here, then it combines nicely with this disjunction, because if we have the negation of X as an element of C, then we can eliminate this disjunction and get that X is an element of B, right? And that will be convenient because we already know that X is an element of A. What we want to prove is that X is an element of the union of the intersection of A and B. So if we can also prove that X is an element of B, then we're basically done. So that's the disjunction introduction, the version of disjunction introduction that we're going to do. We do disjunction introduction on, let me see, this will be line 3, this will be line 4, and now we assume that X is not an element of C. And we put that in a flag. And from this assumption, we now, so this will be disjunction introduction on will be line 5. And so now we need to establish that X is an element of A intersection B. And now we're almost there, because, but unfortunately it's not going to fit, to my regret. I need a couple of more lines than I have. What we still need to do is apply the property of intersection here to get, and so maybe I should sort of zoom out here. If we apply the property of intersection, we can now we basically simplify our goal to proving that X is an element of A and X is an element of B. That's what we need to establish. And then it's a matter, of course, of conjunction introduction. And then we want to prove that both X is an element of A and we want to prove that X is an element of B. So we're going to do conjunction introduction. Oh, I see that that this is something you cannot see anymore. Let me make this a bit better by actually getting this slightly out of the way. There you are. We do conjunction introduction on, well, we don't know yet which lines. Let's first establish X is an element of A. Well, that's easy because we know X is we have this conjunction over here, so we can simply eliminate it. So by conjunction elimination on line 2, we get that X is an element of A. So that's one part of the conjunction that we need. Now we still need to prove that X is an element of B. How are we going to do that? Well, for that, that is a matter of using or actually doing the elimination on the disjunction. And remember, we have here in this context that X is not an element of C. And we also have the disjunction, X is an element of B or X is an element of C. So we can immediately conclude X is an element of B from that. So this is an application of disjunction elimination on 4 and 5. 4 and 5. Basically now our proof is finished. let me at least put this a bit closer, because we don't have a gap in our proof, we don't have a hole in our derivation anymore. Let me fill out some line numbers still. So let's see. This is conjunction introduction on, this will be line 6, and this will be line 7, and this will be line 8. Then this will be line 9, 10, 11, 12. And here we have line 13. Now this is conjunction introduction on 6 and 7. And we have disjunction introduction on 5 and what is it? 9. And then we have universal quantification introduction on 1 and 11. And that's it. So now we have, now our derivation is complete. Let me check the question in the chat. Are properties and definitions both allowed while reasoning up and down? That's a very good question. They are, and for that it matters whether you have an equivalence or a logical consequence. Let me move to my slide, and then it will be clearer. If necessary, I'll move back to the blackboard in a bit. But let's first have a look at the slide that you see over here. Let me move myself out of the way. So here you see the properties that we have just used, and well, the definitions here on the left-hand side, you can consider them to be, I mean, these are definitions on set theoretic level. So you don't, so basically you may, sorry, that holds only for, that holds for the definition of intersection and union. So here you define actually sets. For the definition of inclusion, you may think of that as an equivalence. So you may replace them. So you may you may consider this as this definition as saying that the right-hand side predicate, the universal quantification, is a logical consequence of the inclusion, but also the other way around. So you may use them in both directions. That doesn't hold for the property of inclusion that you see on the right-hand side. Because here we have a logical consequence, and that means that you can only apply this property from top to bottom in your argument, right? So you may if you have this premise, so A is included in B somewhere in your proof, and it is valid, you've already established it in your derivation, and you also have an element of A, then you may conclude that that this thing is also an element of B, but not the other way around. So you cannot conclude from the statement T is an element of B that A must be included in B, right? So it's reasoning from top to bottom if you have a logical consequence. But as soon as you have an equivalence, then you can use it in both directions, right? So so that holds for the property of intersection and also for the property of union. Okay. Let me move back to the blackboard, because there's one more thing that I would like to point out to you before we end the lecture. I wrote a derivation that, besides the logical rules that you've learned so far, so the rules for disjunction elimination and introduction, and conjunction elimination introduction, and the rules for dealing with universal and existential quantifiers, I've also used these properties and definitions of sets. So that is what we now are going to call a proof. And well, there is a slight difference between if we are saying that we require a proof or a derivation. So in the context of set theory, we will always require proofs. And that means that you don't have to be too explicit about the logical rules, the rules for introduction and elimination of logical connectives. So we are going to allow you that if you are giving a proof in set theory, that you omit line numbers, and that you omit mentioning conjunction elimination and conjunction introduction and disjunction elimination and universal quantification introduction. I wrote these things for clarity now, but you will notice that at some point you're so skilled in applying these logical reasoning rules that it's a bit cumbersome to have to write them all the time. What we do require, and let me write that here because it's important that you don't forget it. So that you don't forget it. you may omit, and that holds for proofs. In proofs, not in there. If we require a derivation, then you should mention all these things. Then you should mention the introduction and elimination rules, and you should write the line numbers and the hints and so on. But when it's about proofs in general, as opposed to derivations, references to intro and elin rules. And then I'm only talking about for the logical connectives. So in the end, what we require you to do is, if you have to give a proof of a set theoretic property, then basically we do want to see that you apply and know that actually you're applying the definition of inclusion, and that you are actually applying the property of union, and that actually you apply the property of union here, and the what else do we have? The property of intersection. So what we are going to move into now is to apply the logical reasoning principles that you have learned when you learn derivations more implicitly. What you do, the logical reasoning that you write, has to be logically valid. So we have to understand your logical reasoning, and therefore you still need to apply these logical derivation rules, but you don't have to be explicit about that anymore. What we do need to see is when you actually have you cannot omit the flags, because they have a real meaning, that they're stating an assumption rather than just stating a fact, right? So flags are still important. They introduce an assumption. All right, there are a couple of questions. I'll answer them, and then we'll stop. First question: are you allowed to use the zoom, writing a part that doesn't fit anymore elsewhere method that I use here? You can do that in the test as well, certainly. It's awkward because my iPad, I have to put it in landscape to show you, to make most use of your screen. So if you use an A4, so maybe I can actually show you. I have the, let me do that. So here you see my notes, and it fits here, right? So if you write it on an A4 and you start at the bottom and you write the assumptions on the top, so you start writing the conclusion, the goal at the bottom, and your flags appear on the top, then it usually will fit, especially on tests. The derivation that we require from you fits on an A4 paper, and this is arguably better than this, right? But unfortunately, I have a rather small iPad. This is not to say that of course you can also copy. I hope that you copy my good behavior. If you copy my bad behavior, well, so be it. All right, question: do we still need to write assumes in proofs? No, you could already omit assume in derivation. That was the only hint that we allowed you to omit in derivations. You don't have to write assume. Because that is already, you can already see from the flag what is assumed, right? Can we write the logical reasoning rules but omit line numbers for the set proofs? Certainly, you are allowed to write the logical reasoning rules. At some point you're going to omit them because it's too cumbersome to write them, but I urge you to do that in the beginning, because you're probably not yet very skilled in the logical reasoning part either. So it is good to practice that skill still. So, and it's always allowed to write more things, to give more details in a proof. Then, all right, and then there's the suggestion to repeat the problem for that was in the chat, in the Canvas chat. It was observed by somebody that on 2 pages in the book, and I have to see whether I can actually find my copy of the book here on my computer. Then I would, well, maybe it's actually good to go to Canvas. I posted at some point, I posted there The tables, let me just check whether I actually put it there. So if I'm moving to Canvas now, and I'm going to check whether there. I think I posted the tables there in an announcement at some point, because people were asking for the exercises, and then I also, yeah, there was announced the third announcement of this course. Actually gives a PDF with a couple of tables, and let me try to show you. Actually, let me see. Now I need to find them on my computer. Let me see if I can quickly do that. Because what I wanted to show is that there is a typo in the book. Do we do this? Like this, of course. Okay. Almost there, guys. So I'm looking for the tables on my computer now. There they are. So let me see, is this something you can also see? Not yet. So here you see a PDF that was actually that I actually posted at some point in Canvas, because it's very convenient, a convenient collection of all the rules. And then if you move to the rules for existential and universal quantification, then there's a typo in there. Let me see. So no, where is it? Maybe I actually repaired it in this version. I think there. I think in a. I suspect that I actually repaired it somewhere. Anyway, in the book, let me forget about this then. In the book, there are typos on pages 189 and page 379. It states at some point existential quantification, if I remember correctly, introduction, where it should state existential quantification elimination. Okay, so that's on pages 189 and 379. I'll post an announcement about that just for more clarity. Okay, if there are no more questions, let me briefly check the Canvas chat to see if there's anything that I should still answer. I think there's nothing that there's also the question about the pages 189 and 379. Okay. Oh, there's still a question about failing a weekly test. So and that's a good question. So let me. You don't have to see this anymore. So if you fail a weekly test, so you score less than 5, that is no problem, provided, of course, that you do well on the final exam. So there's a page that explains how we will assess you. The weekly tests, there will be 7 weekly tests. The best 5 grades will count, and will count for 30% of your grade. And there's no requirement that you need to pass every weekly test. There is a requirement that you need to have at least 5 for the final exam. That is important. So if you fail a couple of weekly tests and do very well on the exam, there's nothing lost. If you score less than 5 on the final exam, then you'll fail the course. All right. And as you noticed, on Saturday I posted an announcement explaining that we will only take into account your grade for the first weekly test due to the technical issues that you had to overcome there. If you really benefit from it in your final grade. If you don't, we will discard that grade. And why is that? I mean, completely reasonable from our point of view. Well, we don't consider these weekly tests as part of the assessment in a way. I mean, it contributes only very little to your final grade. 30% is really not much. What it is for is to give you a lot of feedback as the course goes. So you have to, it basically keeps you on track. It makes sure that you study the material when it needs to be studied, because as you now notice in proofs about sets, you need to be skilled in being able to do derivations. And that's why we actually already had a test that's about derivations. So there's such a build-up in the course that you really need to stay focused and stay on top of learning the material as we go, because otherwise you'll get hopelessly lost. We consider these weekly tests as a means to make sure that you do that, and also to give you feedback on how you write things, and they're part of the learning process. They are not parts, they don't constitute a significant part of the assessment process. If you do very well on the final exam, you'll pass the course. I mean, if you score a 10 on the final exam, you can actually score zeros on all weekly tests and still pass the course, right? It's a different matter when you score a low on the final exam, then you can actually be compensated by the weekly tests. So, but we believe in the fact that actually you do well on the weekly tests, and that makes sure that you actually pass the final exam. All right. What are the applications of these proofs for sets? Well, you learn, well, basically what you learn here is to set up a formal system to reason about sets, and the application is that you learn about set theory, right? So, and that will be a very important skill, especially for computer scientists and mathematicians, and also for data scientists. You need to be able to formally reason about sets. And for that, you need to know how to deal with intersections and unions and inclusion, and you need to thoroughly understand that, and at a very precise level. Okay, so still a brief overview of what you can omit in comments. Let me just show you what you need to. So when it's about set theory, then you have to in your hints you have to show that you know the rules of set theory. So these kind of things we need to see. We need to see that you understand you're applying a definition of inclusion, or the property of inclusion, or a property of intersection or of union. And there are a couple of more. There are properties of equality, properties of difference, of complement. Properties and definitions pertaining to sets. That's the things that you need to still mention in comments in your derivations. Okay, is the level of the weekly tests the same as the final test? And that's I think the last question that is still open, and the answer is yes. But you have to realize that basically we build up towards the final test. And then there will be a lot of material that will be tested at this in one single exam, and that makes it considerably harder. But the type of questions of the final tests are exactly the same as the type of questions we use in the weekly test, and you can confirm this yourself by actually looking up the it's a good idea actually to do so by looking up examples of old examinations that we have used in the past, and see that actually the sort of questions that about the material that we have already discussed, like formulating predicates in predicate logic, making derivations, proving that the formula is a contingency, exactly these questions also appear in the final exam. So basically, and that is also something that I hear back from students, is if you prepared for all the weekly tests, then typically there's not a lot you still need to do to prepare for the final exam. If you did all weekly tests well, then basically you're prepared for the final exam. The only thing that you still need to do then is make sure that you sort of brush up your knowledge of the first part of the course, so to speak. I mean, of course, you might have forgotten a bit about what happened in the first part of the course, whereas when you did the weekly test, you had just studied it. Okay, so that's what you need to do. You need to repeat stuff towards the end, but the final test will have questions of the same level of difficulty. Okay, I think that was the last question that I could still answer, and that concludes also this lecture. There are quite a number of videos also in the syllabus specified, and I'll actually I'll post I'll make sure that I'll mention where in the exercise program it would be useful to watch those videos. so that you know how to, and so if you are doing an exercise, you can of course first try to do the exercise, but if you don't manage to solve it, then maybe you want to watch the video first and then solve the exercise, because typically these videos treat examples of proofs in set theory, examples of derivations that we didn't discuss today, but that actually prepare you for making such exercises. All right, let me conclude here. I hope you have a nice evening. Well, I'll see you again next week, or at least you will see me. Good luck with the tutorials, and do the exercises. Bye-bye.